You've probably heard of the God particle, right? And maybe you've seen the Large Hadron Collider pop up in thrillers like Angels and Demons. But you know what? The real story is way more incredible than any fiction. This is about one of humanity's greatest scientific quests, a mission to answer the most fundamental question we can ask.
I mean, really think about that. What is all this made of? For centuries, that single question has been the driving force behind our greatest thinkers. And to finally get a real answer, we had to build the largest, most powerful, most complex machine in human history. A machine designed to literally recreate the conditions of the universe just moments after the Big Bang itself.
Okay, so before we dive into the machine itself, we really need to get our heads around the cosmic mysteries it was built to solve. This isn't just about smashing particles together for fun. It's about tackling a list of profound, totally unanswered questions in physics.
These are the kinds of questions that keep physicists staring at the ceiling at 3 a.m. Seriously, why does anything have substance or mass in the first place? Why are we even here? I mean, for every particle of matter, there should have been a particle of antimatter, and the whole shebang should have been wiped out at the very beginning. And what in the world is this invisible dark matter that we know makes up a huge chunk of the cosmos? The LHC was designed to hunt for the clues to solve these very puzzles.
So for decades, physicists have had this incredible rulebook for the universe called the Standard Model. And it's amazing. It works beautifully, but it had a giant gaping hole in it. It couldn't explain where mass comes from. It was like having a book that describes every single character in a story perfectly, but gives you zero explanation for why they have any physical weight at all.
Right. So to find that missing piece and start poking at those other huge questions, science needed a new tool. A much, much bigger tool. And what they built was a machine of almost unbelievable scale and complexity.
And this wasn't the work of just one country or one lab. The LHC is this extraordinary human endeavor, a testament to what we can actually achieve when we team up on a global scale. We're talking about a planet-wide scientific mission here.
So, to give you a sense of the sheer scale, just picture this. The main accelerator is a 27-kilometer ring. That's about 17 miles, buried hundreds of feet underground beneath the border of France and Switzerland. You could practically run a marathon inside this thing.
And to get it to work, things have to get extreme. The thousands of superconducting magnets that steer the particle beams have to be cooled down to minus 271.25 degrees Celsius. Let me put that in perspective for you. That makes the Large Hadron Collider colder than deep space. It is literally the coldest large-scale place in the entire universe that we know of.
And inside this unbelievably cold tunnel, tiny protons are accelerated to 99.999999% of the speed of light. They move so ridiculously fast that they whip around that entire 27-kilometer ring over 11,000 times, every single second. It's just mind-boggling.
So when you put it all together, you get a machine of absolute extremes. It's the biggest, most powerful particle accelerator ever built by humankind. It smashes particles together with an energy of 13.6 tera-electron volts. That's trillions of times more energetic than visible light, all to get a peek at the very fabric of reality.
But you know, the particles don't just jump straight into the main ring. It's more like a multi-stage rocket launch. They start their journey in a linear accelerator, and then get handed off to a series of bigger and bigger rings, each one boosting their energy and speed until finally they're ready to be injected into the two main LHC rings, flying in opposite directions, ready for the main event.
Which brings us to the LHC's #1 mission. All this incredible technology, this massive global effort, this 20-year-plus project, it was all focused on finding one incredibly elusive theoretical particle, the missing piece of the Standard Model. This was the hunt for the Higgs boson. So after the first high-energy collisions started in 2010, scientists just began sifting through mountains and mountains of data. By the end of 2011, these tantalizing little hints started to show up. The excitement just kept building until one historic day, July 4th, 2012, which led to one of the most important scientific announcements in a century.
And this was it. This was the moment. You know, scientists are always super cautious with their language, but what this really means is, we found it. After decades of searching, the evidence was finally there. They discovered a new particle, and its properties were a perfect match for what they expected from the Higgs boson.
Okay, so why is this such a huge deal? Well, because finding the Higgs boson proves the existence of the Higgs field, an invisible energy field that permeates the entire universe. As other particles move through this field, they interact with it, And that interaction is what gives them mass. Without this field, particles would just be weightless specks zipping around at the speed of light. Nothing, not atoms, not stars, not planets, not you or me, could ever have formed.
But hey, the LHC is no one-hit wonder. It has also managed to create something called quark-gluon plasma, which is this super hot, dense soup of matter. That's basically what the entire universe was made of moments after the Big Bang. And it's discovered totally families of particles, these exotic combinations called pentaquarks and tetraquarks. We didn't even know for sure they could exist.
So, with the Higgs boson found and the Standard Model looking complete, is the story over? Do we pack up and go home? Not even close. In fact, the LHC is now pushing into brand new frontiers, searching for physics beyond our current rulebook.
This chart really shows you where physics is at right now. On the left, that's the solid ground we're standing on, the Standard Model, which the LHC helped complete. But on the right, that's the great unknown. That's the cosmic mystery tour we're on now. Scientists are using the LHC to hunt for signs of brand new physics, like supersymmetry or the actual particle that makes up dark matter, and even, get this, evidence of hidden extra dimensions.
And to help with this new quest, the LHC is getting a major upgrade. It's called the High Luminosity LHC, and it's basically going to crank up the number of particle collisions by a factor of 10. I mean, the more collisions you have, the better your chances are of seeing something incredibly rare pop into existence, something that could signal brand new physics.
So, the story of the Large Hadron Collider is far from over. In a lot of ways, it's really just beginning. It answered one of the biggest questions of the last 100 years, and in doing so, it opened up a whole new set of even deeper mysteries just waiting to be solved. The adventure absolutely continues.
Finding the Higgs boson was just a monumental achievement, a capstone on a century of physics. But it also turned out to be a doorway, a portal to a deeper, stranger, and more wonderful universe than we ever imagined. The real question is, what will we find when we step through? What secrets are we going to unlock next?